Today, we're going to talk about the economics of data, designing cost-efficient, high-impact data platforms. Let's start with a simple reality check. Most companies today have some kind of modern data stack. There's a data warehouse, maybe a lakehouse, some streaming, a BI tool, an orchestration layer, a catalog, a dashboard for everything. On paper, it all looks impressive. The slides are beautiful. The architecture diagram has so many logos it could be a startup conference banner. And then the cloud bill shows up. Someone in finance forwards it around and asks a very uncomfortable question. Are we actually getting enough value from all of this? That's the question this entire video is about. Not just how do we cut costs, but something deeper. How do we design data platforms that are cost-efficient and also high-impact? How do we make sure our pipelines, warehouses, streams, features, and dashboards make economic sense, not just technical sense? This is especially important if you're a data engineer, machine learning engineer, analytics engineer, or architect. Because the people who will grow into staff, principal, and head of data roles are not just the ones who know the tools, but the ones who can connect infrastructure decisions to business outcomes and costs. So in this video, we're going to build a mental toolkit. We'll talk about where money actually goes in a data platform, how to reason about cost versus value, how to spot economically bad designs, and how to refactor toward more efficient ones without killing innovation or speed. Before we go into cost, we need to agree on what we mean by data platform. When I say data platform, I don't mean one specific tool. I don't just mean the warehouse, or the Kafka cluster, or the ML pipeline. I mean the entire system that takes data from the real world and turns it into something that humans or machines can use to make decisions or predictions. In practice, that usually means you have sources, application databases, event logs, click streams, mobile apps, back-end logs, third-party APIs, SaaS tools, maybe batch file drops from partners. You have ingestion, change data capture jobs, streaming consumers, batch ELT pipelines, connectors that pull or receive data. You have storage, a data lake or lakehouse on object storage, a data warehouse with structured tables, sometimes operational stores or feature stores for ML. You have transformations, dbt models, SQL transforms, Spark or Flink jobs, notebooks converted into scheduled pipelines, ML training workflows that reshape and join data. You have serving, dashboards, self-service BI, internal tools, data APIs, batch exports, model inference pipelines. And you have governance and observability, data catalogs, quality checks, lineage, logs, metrics, alerts, cost dashboards. All of that together is the data platform. And all of it costs money. In compute, in storage, in network, in licenses, and in engineering time. To think about the economics of this platform, let's introduce a very simple model you can use for anything you design or operate. Cost, value, and shape over time. First, cost. What does this thing actually cost to exist? That includes compute, jobs, clusters, queries, storage, tables, backups, replicas, network, data transfer, egress, SaaS licenses, and also human cost, engineering hours, on-call time, incident response, manual fixes, and maintenance. Second, value. What outcomes does this thing enable? Does it power a revenue-generating product feature? Does it feed a model that improves conversion or reduces churn? Does it enable a critical report for leadership? Does it satisfy a regulatory or compliance requirement? Or is it basically a nice-to-have just in case someone wants this dashboard someday? Third, shape over time. How does cost and value evolve as the company grows? Some designs scale almost linearly with data volume or traffic. Others explode. double the data, and suddenly your costs triple or worse. On the value side, some pipelines get more valuable as more teams adopt them or as more models use them. Others plateau quickly. This gives you a powerful lens. For any job, dataset, feature, or dashboard, you can ask, what is the cost? What is the value? And how does that relationship change as we grow? It's not about being perfectly precise. Even rough reasoning is much better than ignoring economics completely. Now let's map out where money actually goes in a data platform. Think of your spend as being split into a few big buckets. First, ingestion and movement. That includes streaming infrastructure like Kafka, Kinesis, Pub/Sub, managed streaming services. It includes connectors for pulling from databases or SaaS tools, and jobs that do ELT or ETL into your lake or warehouse. Many teams underestimate how much always-on ingestion and high-throughput streaming can cost over a year. Second, storage. You pay for every gigabyte or terabyte sitting in your data lake or warehouse. That includes raw data, intermediate tables, curated marts, backups, versions, and replicas. Premium warehouse storage can cost more than low-level object storage. And if you keep everything forever at the hottest tier, that adds up. Third, compute for transformations. Every nightly batch job, every DBT run, every Spark or Flink pipeline, every backfill, and every heavy transformation query consumes CPU, memory, and I/O. This is often one of the biggest line items. Fourth, serving and querying. The BI tool queries the warehouse. Data scientists run ad hoc queries. Services call low-latency APIs or feature stores. Every query that scans large tables or complex joins is effectively burning money. Fifth, network and data transfer. Cross-region transfers, egress out of the cloud, data movement between services and layers. This can be surprisingly expensive at scale, especially if your architecture is very chatty across boundaries. Sixth, tooling, observability, and governance. Catalogs, quality platforms, data observability services, specialized ML monitoring, and so on. Many of these are licensed per seat, per volume, or per environment. And finally, people. People are actually the biggest cost in most real-world scenarios. If a pipeline constantly breaks and requires hours of debugging, it might be cheap in compute but extremely expensive in human time. If your platform is fragile and noisy, on-call fatigue and incident load quietly become part of your data economics. One of the most important economic decisions you make in a data platform is choosing the right workload pattern, batch, streaming, or interactive. Let's start with batch. Batch processing runs on a schedule. You might have hourly jobs, daily jobs, weekly jobs. This is usually easier to reason about. You know when it runs, you can cap resources, you can manage concurrency. For many use cases, financial reports, daily metrics, training datasets for models, batch is not only enough, it's the most cost-efficient choice. Streaming, on the other hand, is always on. Events are processed continuously as they arrive. This is powerful when latency really matters. Fraud detection, real-time personalization, live leaderboards, real-time monitoring. But the economic trade-off is that always-on processing and streaming infra runs 24/7, whether or not your business truly needs millisecond or second-level freshness. Interactive workloads live in queries run by humans or tools, analysts trying things out, data scientists exploring, dashboards sending on-demand queries. These are flexible and crucial for insight, but can be economically dangerous if unconstrained. A handful of select from giant table queries, repeated all day, can dominate warehouse cost if nobody is paying attention. A cost-aware engineer doesn't ask batch or streaming, which is cooler. They ask, what freshness does this use case really need? If a dashboard is fine with data that's 15 minutes old, you might not need full-blown streaming. If the use case is only sensitive to daily trends, an hourly or daily batch job may be far more efficient than a complex, always-on topology. Let's talk about data modeling and physical table design, because this is one of the biggest levers for cost. When you design a schema, you're not only optimizing for clarity, you're also shaping how much data gets scanned for each query, how much storage is duplicated, and how often work is repeated. Partitioning is the first tool. Large tables are often partitioned by date or another high-level key. Good partitioning means that most queries can skip huge chunks of data. Bad partitioning means either scanning too much or creating millions of tiny files and overwhelming metadata layers. Over-partitioning creates operational overhead. Under-partitioning creates constant waste in query scans. Clustering or sorting helps group related rows together. If your queries filter by user ID or region, sorting on those can dramatically reduce I/O. But maintaining clustering also costs compute and complexity. The trick is to use it where the read patterns justify the right overhead. Denormalization versus normalization is another big economic choice. Highly normalized schemas can be beautiful academically, but require many joins to answer business questions. Those joins can be expensive at scale. Denormalized marts and wide tables duplicate some data and use more storage, but can drastically reduce compute per query. Often, for high-traffic dashboards, denormalized marts are economically better than repeated heavy joins against normalized models. Materializations like pre-computed aggregates are also part of the story. Instead of recalculating the same aggregates in every dashboard, you can build a single scheduled job that generates a fact table of daily metrics or rolled-up statistics. You pay more compute during the batch run, but you save a lot on interactive query cost and improve performance for users. Storage strategy is another area where economics matter more than people realize. Storage is cheap per unit, but cheap times enormous volume times no retention discipline becomes very real money. A helpful way to think about data is by temperature: hot, warm, and cold. Hot data is used frequently and needs to be fast. This is recent events, current state, up-to-date dimensions, features used for online inference, the last weeks or months of core metrics. Hot data belongs in your most performant, most accessible layers: warehouse fact tables, primary marts, hot feature store keys. Warm data is accessed occasionally. Maybe you only look at the last year of detailed transactions when doing quarterly analysis or when debugging a trend. Warm data can live in slightly cheaper, less optimized forms. It might be stored in a lake with decent but not perfect indexing, or in aggregated historical tables. Cold data is rarely accessed. This could be raw logs from 2 years ago, detailed clickstream data from 5 quarters back, or legacy system exports you keep for compliance. Cold data can be compressed heavily and moved to the cheapest storage tiers, where retrieval is slower and less convenient, but that's okay, because you hardly ever need it. A cost-efficient data platform sets clear policies: how long data stays hot, when it's downsampled or aggregated, when it's archived. It also periodically reviews usage. Which tables do people actually query? Which data is just hoarded, just in case? That combination of policy and observation is where a lot of hidden savings live. Now let's introduce the idea of cost observability. It's not enough to optimize once. You need to see and understand how cost is behaving continuously. Cost observability starts with tagging and ownership. If you can tag jobs, queries, tables, and clusters with team names, product lines, or domains, you can break down spend per team or per business domain. That immediately changes the conversation. Instead of one giant, mysterious bill, you can say, analytics costs this much, ML training costs this much, marketing pipelines cost this much. Next, you want visibility at the level of jobs and queries. Which queries scan the most data? Which scheduled jobs use the most compute? Which tables are growing fastest? Without that, cost is a black box. With it, you can point to specific hotspots. This job costs 10 times more than any other. We should look at it. On top of that, you build dashboards and alerts. You can alert when warehouse spend spikes unexpectedly, when a table's size grows suspiciously fast, when a job's runtime doubles from one week to the next. Cost anomalies can be treated just like performance anomalies or error spikes. They trigger investigation. Finally, you institutionalize periodic reviews. Once a month or once a quarter, someone looks at the top N most expensive queries, the top N most expensive jobs, the fastest growing tables. Many extremely simple changes, adding a filter, adjusting a partition, limiting retention, caching a result, can have a large impact once you know where to look. Of course, cost alone is not the full story. You build data platforms to create value. The interesting part is the relationship between cost and value. It's useful to classify pipelines and workloads into 4 rough buckets. High cost, high value. These are essential. Maybe it's a recommendation model that directly affects revenue, fraud detection that prevents losses, or core executive dashboards. These should exist. The goal is to keep them as efficient as reasonably possible while respecting the high-value SLAs. Low cost, high value. These are your golden assets. A small, simple daily metric that everyone uses. A compact dimension table used across many pipelines. These deliver tons of value for not much spend. Protect these and keep them reliable. High cost, low value. This is where you have a problem. That could be streaming pipelines feeding dashboards that no one actually checks. Or a complex experimental ML pipeline running every day long after the experiment ended. Or a huge detailed data set that only one person uses once a quarter. These are prime candidates for redesign, simplification, or deletion. Low cost, low value. Small, cheap pipelines that don't do much. They're not urgent problems, but they clutter your mental model and your platform. Over time, even low-cost noise can become a maintenance burden. As an engineer, one of the most powerful questions you can ask is, what would actually happen if we turned this off? If nobody can tell you clearly, or if the answer is, not much, then you've found a workload whose value is questionable. Let's look at some common anti-patterns in data platform economics, because recognizing these in your own environment is a big step forward. The first is stream everything. A team adopts streaming technology, and suddenly everything becomes a real-time topic. Orders, clicks, user updates, metrics, logs, experiments. Some of those really benefit from low latency, but many don't. You end up with a forest of consumers and jobs, all running 24/7, powering dashboards that could be refreshed every 15 minutes or once an hour with no business impact. The cost of that enthusiasm shows up later as high streaming bills and operational overhead. The second is warehouse as junk drawer. All data ends up in the warehouse, raw and unstructured, with no clear life cycle. Analysts query raw tables directly. There are no curated marts or semantic layers. Queries scan billions of rows repeatedly to answer simple questions. This is easy to build initially, but economically painful over time. The third is zombie pipelines. These are pipelines that were built for a specific project or experiment and then never cleaned up. The model might not be in use anymore. The dashboard may be abandoned. But the job keeps running, the data keeps being written, and the platform keeps paying for it. No one really owns it. It just lives on, quietly consuming resources. The fourth is hero dashboards. A single critical dashboard with very complex logic, hitting many large tables directly. It was built quickly to answer a question for leadership, but now it's used widely. Because there's no underlying curated model, every refresh is expensive. When something breaks, debugging is slow because the complexity lives in the dashboard queries instead of reusable data models. Now let's flip this around and talk about healthier patterns. Refactors that can improve data economics while maintaining or even improving usefulness. One pattern is streaming to batch, where appropriate. You identify a streaming pipeline that feeds a use case not truly requiring second-level latency. For example, daily operational metrics or near real-time dashboards where a 5 to 10-minute delay is perfectly acceptable. You redesign the pipeline as a scheduled batch job or micro-batch approach instead of a full-blown streaming topology. You reduce always-on compute and simplify operations. Another pattern is from raw queries to curated marts. Instead of having every dashboard and ad hoc exploration query raw event tables, you create a set of well-modeled fact and dimension tables. For example, you create a fact orders table with all the logic around status, currency conversion, and returns already baked in. Then, dashboards and analysts query this table instead of raw logs. Over time, this reduces duplicated logic, reduces scan volumes, and improves reliability. A third pattern is cold storage offloading. You examine your largest tables and split them by age. Keep recent periods in hot, highly optimized formats. Move older periods into cheaper storage or into aggregated historical tables. You also update queries to default to recent data, with explicit options for longer history when truly needed. A fourth pattern is shared feature engineering for ML. When you see multiple teams recomputing similar features in separate pipelines, you consolidate them into shared feature pipelines and a feature store or central feature table. You compute once, reuse many times. This saves compute and also reduces subtle inconsistencies across models. Guardrails are another essential ingredient in a cost-aware platform. Instead of hoping everyone will behave optimally, you design the platform so that the default behavior is safe and efficient. One type of guardrail is resource limits and quotas. You can set max query runtimes, scan limits, concurrency caps, or cluster size limits. This doesn't mean nobody can run heavy queries. It means they have to be intentional about it. They might need to request higher limits or use special environments for extremely large workloads. Another guardrail is safe defaults. For example, you can design queries, dashboards, and tools to default to a recent time window, say the last 30 days, rather than the entire history of a table. You can encourage exploration on sampled or aggregated datasets instead of full raw logs. You can make the easy thing also the cheap thing. Access control can also be a cost guardrail. Restrict direct access to the heaviest raw tables to a small group of advanced users, while encouraging everyone else to use curated marts and views. That's not about locking people out. It's about steering most usage toward more efficient layers. Templates and golden paths are another subtle guardrail. When new engineers or analysts want to build a pipeline, you give them recommended patterns. How to structure code, how to choose a schedule, how to add monitoring and tagging. If those templates are cost-conscious, the platform naturally grows in a more economical direction. Let's talk specifically about ML and LLM-related workloads, because they add new dimensions to the economics of data. For traditional ML, there are three major cost buckets: training, inference, and data pipelines. Training can require large clusters or GPUs, but it's often periodic. Inference is ongoing. The more traffic you have, the more you pay for serving. Data pipelines, feature engineering, data preparation, feature stores, tend to run both offline and online, and can quietly become large, steady costs if not designed carefully. When you move into LLMs and retrieval-augmented generation, you introduce vector stores, embeddings, and retrieval pipelines. You pay for embedding generation, for storing large vector indexes, for queries against those indexes, and for keeping the underlying knowledge base fresh. The quality of your data and retrieval logic often has more impact on product quality than just upgrading to a larger base model. A cost-aware ML or LLM engineer asks questions like, Do we really need this feature in real time, or is hourly enough? Do we need to re-embed everything all the time, or can we only embed changes? Does this model need to be the largest possible variant, or is a smaller one plus better features enough? Can we cache results and reuse them instead of recomputing every time? The same cost-value-shape logic applies here. For each model and pipeline, what's the cost, what's the value, and how does that change as usage scales up? So what can you, personally, start doing differently as a data or ML engineer? First, connect everything you build to a real consumer and a real use case. Before you design a pipeline, ask, who will use this table or feature? How often? For what decisions or predictions? What freshness do they actually need? This alone prevents a huge amount of over-engineering. Second, estimate cost early, even roughly. When you define a new table, think about how big it might get over time. When you define a schedule, think about how often it will run. When you propose a new streaming pipeline, think about the 24/7 cost versus a periodic job. You don't need perfect numbers. Even this will probably be expensive versus this is likely cheap is enough to guide design. Third, learn the billing and pricing model of the tools you use. Know how your warehouse charges, per query, per TB scanned, per compute unit. Know how your storage tiers are priced. Know how streaming throughput, partitions, and retention affect cost. That knowledge is like X-ray vision for your architecture decisions. Fourth, make cost and reliability part of the definition of done. When you finish a pipeline, make sure it is tagged with an owner, monitored for failures, and visible in cost dashboards. Treat big cost regressions like you'd treat performance regressions or SLO violations. Fifth, practice communicating in business language. Instead of only saying, this pipeline is slow, you can say, this job costs roughly this much per day, enables these metrics, and we can reduce its cost by about 40% by changing X. That kind of communication builds trust with leadership and makes it easier to get buy-in for refactors and improvements. Let's close by stepping back to the big picture. A data platform is the engine that turns raw data into decisions and predictions. It's easy to focus purely on technical questions. Can this scale? Is this real time? Is this using the latest cool technology? But the platforms that survive and thrive are those that also make economic sense. They create more value than they consume. They support more and more use cases without their cost curve exploding uncontrollably. They are understandable, operable, and intentional. In this talk, we've walked through a way to see your platform not just as architecture diagrams and tools, but as an economic system. We've talked about where money actually goes: ingestion, storage, compute, network, tooling, and people. We've introduced a simple framework. Think in terms of cost, value, and shape over time. We've looked at workload patterns, modeling choices, storage strategy, cost observability, anti-patterns, and healthier refactors. We've applied the same logic to ML and LLM systems, where data and infra decisions are tightly coupled to business economics. The core mindset shift is this: don't only ask, can we build it? Also ask, is this the right way to spend money to get this outcome? As a data engineer or ML engineer, when you start asking and answering that question, you stop being just a pipeline builder or model trainer. You become a designer of economic engines for your company. And in the long run, that's where a lot of impact, influence, and opportunity lives.